All right, so my name again is Dave Johnson. I run Informatics for Moderna. So my job is to support all of research from preclinical through clinical with digital and automation enabling solutions. And while Lab of the Future is a heavy lift to live up to, I'm going to do my best here and talk about the work that we've done over the last number of years around high-throughput production of preclinical mRNA. If you're not familiar with Moderna, what we're trying to do is build a whole new class of medicines based around mRNA technology. The central dogma of biology is that the information to create every protein in your body is encoded in your DNA. mRNA is what carries that information from the nucleus out to the ribosomes, which will then produce whatever protein they're instructed to. And so what Moderna is trying to do is we create our own synthetic messenger RNA that encodes whatever protein that we instruct it to, that gets carried to the ribosomes in the cell. We typically encode, let's see if that works. We typically wrap those mRNAs inside of a lipid nanoparticle, which you can see here. That when it reaches the cell, will inject the mRNA into the cell, the ribosomes grab it, and then print off whatever they're instructed to. What's really cool about this is with the same technology, the same process, just with mRNA where we encode different information on that, we can produce a variety of different kinds of proteins. So you can see here secreted proteins, transmembrane proteins, mitochondrial, ER, nuclear proteins. Anything your body can produce, we can encode that into an mRNA. But we can also encode all sorts of other things like antigens to create vaccines. So anything at all that we can encode, we'll put into an mRNA. What this gives us is a really flexible, programmable platform for creating medicines. And what we've done is, in the short lifetime of what is a rather small company in this industry, we've amassed a rather huge pipeline, really unprecedented for the size of what we have. We have 22 candidates in development right now, most advanced of which is VEGF, which is a partnership with AstraZeneca in phase 2. But we have prophylactic vaccines. We have 2 different cancer vaccines, one of which is a personalized cancer vaccine where we sequence an individual patient and produce a vaccine just for that patient. We have intratumoral, we have localized regenerative, we have systemic secreted, intracellular as well. Anything that we can think of and target, we are actively pursuing. So you can see there's just a huge variety of different applications across our development pipeline here. If you look at the 10-year vision of the company, our goal is, not unsurprisingly, is to be the leading mRNA company. And we continue to invest in that. We invested heavily for the future, and we'll continue to do that, working with our partners to discover and develop a huge breadth of meaningful vaccines and therapeutics. But the next one is really key for me as part of the digital function is that we integrate automation and digital technology into everything we do. It's not just in certain isolated areas, it's not just manufacturing, it's across research, across the business, across finance, wherever we can apply it, we do that. Ooh, too far. And we think about digital and how it applies. There's a number of foundational building blocks that we use. And we start with the cloud. Obviously, we're heavily based in AWS. They wouldn't have invited us here if it wasn't for that. But we've been an AWS user from the early days. Very early on in the company, we started using it. And our mantra is to put as much in the cloud as we can to leverage the benefits of that shared infrastructure. We do, of course, have some on-prem stuff for low latency activities and storage for instruments that we have to have. But whatever we can, we push it to the cloud. And it goes beyond infrastructure. We also work with all of our software vendors who have SaaS solutions. We tend to prefer SaaS providers, let them host and manage their own infrastructure, where they'll do a better job of that than we can do. The next level is integration, which is almost always forgotten about in the enterprise. We have probably hundreds of different applications, and wherever we can, we integrate that data together. It's very uncommon that an application exists in a silo where its data is just for itself, right? So what happens if you don't integrate is you have humans, people, putting the same information in every single different system, which is incredibly error-prone, but it's also incredibly tedious for those users. And so you end up doing things like offshoring that activity, looking to RPA because you should have just integrated it in the first place. And we do this everywhere. We see some of our more advanced integrations in things like onboarding people, onboarding new people when we hire them. Right? That's information needs to touch dozens of different systems. So we have one user record that's input, and it floods out to the various different systems. Next, we move into Internet of Things, which are any kinds of devices, any kind of PCS in manufacturing, any kind of sensors. We have a bunch of Amazon IoT buttons that we use for inventory replenishment and manufacturing. So any dumb device that we can get connected to the internet, we will to collect data. Then we move into more sophisticated automation robotics platforms. And I'll talk about some of this later with the liquid handling robots. These are much more sophisticated robotic platforms with kind of movable arms and movable pipettes that can take instructions and relay data back. And then finally move into the analytics and AI space, where we take all that data that we're collecting from our data capture systems and process automation. We reflect that back to the users in terms of just basic reports, basic metrics, KPIs. Then we start to get into more advanced applications and algorithms where we're starting to make decisions on behalf of the users and take them out of the loop in a lot of cases. And I'll touch on some of that. So as I said, I'm responsible for supporting research. And if you look in the kind of early stages of research, this is kind of a cartoon of what the cycle looks like, right? A scientist would formulate a hypothesis about some target they might be interested in trying some mRNA for. Here's a protein I think that would work really well for this disease. So they formulate that hypothesis. Then they need some mRNA to test that. So they'd have to go and synthesize, create the messenger RNA for that. They'll run an experiment to see what the outcome of that is. They'll evaluate those results, and they'll tell them what to do next. Right? Do I run another one? Do I abandon this and try something else? So there's bottlenecks across all of this, but very early on in the life of the company, we identified synthesis of mRNA being one particularly ugly bottleneck that could slow this process down. And 5 years ago, we did make the decision right away to say we should centralize this. Right? So we have one group, this preclinical production group, who's responsible for producing mRNA on behalf of the rest of the company. But it was a very manual process. With the staff that we had at the time and the process the way it was, we were limited to about 40 unique mRNAs in a month. Now, it's 40 new drugs, right, potentially in a month, so it's still pretty good. But it wasn't great, and we knew we could do better. So what we wanted to do was really accelerate the pace of research by doing better in this space. So we thought if we could decrease the synthesis time to make it faster from when a scientist says, I need an mRNA, to when we get that mRNA, that lets them perform that cycle over again. They get their experiment done faster, they get the results faster, they can move on faster. If we can increase the quality and the consistency of the mRNA, we take out the guesswork from the scientists. When they get a bad experimental result, they're not saying, well, was it a bad experiment or was it bad mRNA, right? We take that out of the picture, and we let them run repeat experiments where they run 6 months later and they can actually trust that the mRNA they got that time is equivalent to what it was before. And then finally, most importantly, if we can increase throughput, we can dramatically improve this. So instead of having only 40 scientists who potentially ask a question a month, we can have many more ask it. We can have a scientist test multiple hypotheses at once, right? Maybe here's 5 different targets I'm interested in. We also do a lot of codon optimization, where we are actually mutating the mRNA to change the nucleotides but leave the protein the same, such that we get different expression or different manufacturability. And so letting a scientist run an entire panel of codon-optimized variants and see which one works best. So by driving these 3 points home, we can really dramatically improve the pace of research. So I'll fast forward to where we are today. And we've been here for a bit now. We have this high-throughput preclinical production facility. It was in Cambridge, actually on Bent Street, but we recently, last year, moved into our new Norwood manufacturing facility. It's a 200,000 square foot manufacturing facility that's mostly dedicated to GMP manufacturing. But on the second floor of this facility, there's a space carved out where we've moved in our preclinical production. You can see here on the bottom, it's a heavily robotic process, lots of robots and cool instruments there. And as opposed to 40 mRNAs a month, we now have the capacity of producing up to 1,000 unique mRNA, never before made, ever, in a month. To do this, we have lots of robots and lots of robotic pieces of equipment, but we have quite a few that are actually integrated in terms of web service integrations. The workhorse we have are Hamilton liquid handling robots, which are these gray boxes up here. These are kind of general purpose liquid handling platforms. You can reconfigure the deck, you can attach different equipment on the sides of these, and they take variable instructions for what to do. We have 13 of these active in production across the company. We probably have over 20 of them. Within production alone, we have 65 different methods. So there's 65 different kind of unit operations that these robots perform. Things like preparing a plate for an assay. We have a bunch of zebra label printers. We have 3 of these robotic freezers that store tubes of material at various stages in the process. We have 2 -80 Hamilton SAM freezers and 1 -20 Lyconic freezer. The frustrating thing about all of these, they're all integrated, but they all speak an entirely different language. The Hamiltons don't have any notion of a web service, but they can actually make outgoing HTTP calls to get information. The zebra label printers expose a TCP socket you can connect to. The SAM Hamilton freezers, they expose a SOAP API, and the Lyconic exposes a REST API. So we have 4 different integration techniques here that we have to just deal with. But it's better than most of the instruments which don't integrate at all. So let's see. We made an early decision to push as much of the logic as we can into the web application layer. And the reason for that is because deploying 65 different methods across 13 different lab PCs is a real pain in the neck to get done. We've done a lot of work just to keep them up to date with the methods the way they are. But we have lots of frequent changes that we do, and so it's a huge challenge to do that. So instead, we push as much up into the web application layer. So what tips to use, where to put materials, what materials to use, what incubation times, all of that is kept up in the web application layer. And we keep the methods as dumb as possible so that they don't have to be changed as much. And it's a two-way stream. The Hamiltons will reach out and say, what am I supposed to be doing? They will do those activities, and they often have attached quality control instruments like concentration or pH meters that are directly attached to them, and they'll feed that data back up for capture and analysis. On the right here, you can see some screenshots of the plate maps from the web application, which is instructing the Hamiltons exactly where to pipette different materials. The different colors here, it does not show up at all. The different colors here indicate different orders from scientists. So this is a graphical picture of a 96-well plate. It's about that big with 96 little buckets that we make mRNA in. Depending on the order, you get more or less wells on that plate, and they get pooled together at the end. And what's really cool here is the different colors are different orders. So the first one might be an oncology drug. The next one might be a vaccine. The next one might be a rare disease, all running together through the same process at once. And on the right there, you just see the next scale up, which is much larger in these larger labware. So this application that communicates and drives this production process is actually part of a broader integrated suite of informatics applications that we have. These are built on a microservices-based approach, so they tend to do one thing and one thing only. This is a snapshot of just part of them. We have applications for supporting clinical, for supporting research, in vitro and vivo studies. But these are the relevant ones for production of mRNA. And it starts really at this mRNA design tool on the top here, where scientists can build and design their own mRNAs by combining different blocks, mutating things, running codon optimization algorithms. Then they order the mRNA, say, I want this one with these attributes, and I want you to deliver it to me here. It's integrated with our finance system, SAP. It's all internal users, but we cross-charge departments so that if you order some huge amount of mRNA, your department gets hit for that. Those orders flow to production. It integrates with those robotic instruments. We have an application called Pipeline, which does Sanger sequencing analysis. I'm going to dig into that one a little bit more in a minute. We have external vendors we work with. So they do either provide raw materials that we need for part of the process, or they perform some quality check analysis, some assays for us. And of course, like the robots, they all have their own integration layers that are different. So we have our own application that sits in front of that. We integrate label printers. We have an application for just managing the quality control process, where you take a sample of final material, you send it to this other group, and they analyze it. We have sample inventory. We even have a shipping application that deals with the logistics of taking that mRNA and shipping it over to Cambridge. And then finally, we have email. All of these applications are deployed in Amazon. So we have an AWS virtual private cloud. We put everything in Docker containers and deploy to AWS Fargate. We're an early adopter here, and we've moved our entire production suite into Fargate now. We have no EC2 servers running production workloads anymore. Across all of the services we have 180 different tasks. These are different Docker containers that are running. So we have the different applications. We have a proxy layer. We use an Amazon load balancer in front, and we use Elasticache for caching, and RDS as our database. And what's really great about this picture is everything has multiple instances of it. There's at least 2 of everything. Some have across all 6 data centers. And it's all self-healing. So if anything dies, any single application, it automatically gets replaced. And it does happen. It's just randomness of it. And so we don't have to think about the infrastructure. We don't have to think about patching these servers, which we used to have to deal with. We don't think about disk running out on the server. So getting rid of that entire infrastructure layer and having my guys focus purely on developing applications to support the business. So the last thing I want to do here is dig into one particular example of how we do kind of data integration automation. Now, across this whole production process and across the company, we have numerous algorithms, numerous automated processes, but I wanted to dig into one just so you can kind of see end to end what one looks like, and then show you what an ROI for one of these is. So we do a lot of Sanger sequencing analysis, like a lot. If you're familiar with NGS, Sanger is the old generation sequencing, but it's still heavily used by any DNA-based, any protein-based, RNA-based company as a really cost-effective way to quality control sequences and to verify that a sequence actually is the DNA sequence it's supposed to be and it doesn't have any mutations. So the way it works is you have some sample of DNA and you run it through a sequencer. That sequencer will run through a thermocycle process to extend the mRNA with these die-capped ends, and then it will run it through capillary electrophoresis and shine lasers on it. And what you get is these peaks of intensity that signify the different bases. And so then you can just read off that's an A, C, G, or a T, right? That data is noisy like all data. It also only covers part of the sequence. You usually only get about 500 to 700 good bases read out of it. So you end up staggering these reads across in both directions. So in order to make sense of that data, you actually have to run it through some software that will identify all the peaks, it'll call the peaks, it'll line them all up together, it'll say, what is the consensus? It has to compare it to what it's supposed to be and say, aha, I found a mistake. This base is not what it's supposed to be. And then it'll pass or fail the sample, right? Now, the challenge is, and this is how we did it in the early days, this software is almost always Windows-based software with a graphical interface. So a user or an operator would essentially have to take a zip file that comes back from the vendor who runs the assay for us. And in there is every single well of a 96-well plate, so 96 different data files. They have to pull out the ones that are relevant to just that sample, load it into the software, go get a FASTA file, load it in the software, and then run the analysis and then decide what to do. So it's a hugely manual, tedious process. And on top of that, we're at kind of a level of control here where the software doesn't look for things that we're concerned with. We're really concerned about itty-bitty little problems like mutations in a subpopulation of the DNA rather than in all of it, and a bunch of other little edge cases that we've run into. And so that off-the-shelf software doesn't really work for us. So what we did is we built this automated data processing framework for just Sanger sequencing. Over here on the left, we have a sequencing vendor who actually runs the assays. We send them plates of samples, and they'll run it through their sequencers. And we do this outside of the house because it's really a commodity to run Sanger. So you can go for the cheapest supplier for that. What they do is we actually give them an IAM credential to load that data directly into our S3 bucket at the end. So they have a LIMS system that will push that data up. The moment it hits, it triggers an S3 event. That event gets pushed into an SQS queue, which is just a work queue of all the samples that need to be run, all the data files. This Sanger app will then read that message that says, hey, go process this data. It'll pull the zip file out, and then it'll open the zip up, find the reads that are relevant, tie it together with the data, and then it submits it to this internal clustering software we have that will spin up spot instances on demand, as many as we need to process the data in parallel. And then we'll run a proprietary Sanger QC algorithm that we have running in Docker containers that will then process that data and make a pass-fail call. The results of that are pushed into an SQS queue for receipt back. The application pulls it forward, and then it'll go to the production app and say, hey, that lot of material is failed. Just kill it off. So the numbers here, as I said, we run a lot of Sanger. A typical day, we run 300 or 400 samples through 300 or 400 analyses. Over the last 4, we've run over 200,000 analysis. That's over 2 million different wells, 2 million different data files we've processed. Conservatively, if you do back-of-the-envelope calculations, we've probably saved a couple FTEs every year who would just be dedicated purely to looking through Sanger data, and they would have to not want to quit their job from looking at Sanger data all day. So it's likely higher than that. But we also get much improved quality here, right? Because we don't have subjectivity of one operator saying, that looks a little rough to me, I'll fail that one, right? It's clean, it's consistent, it's always the same. And so what does this all cost, right? So I didn't look up the storage cost because that would be the same regardless of the solution, but I looked at what the compute cost is for the dynamic scaling of this over the last 4 years, and it comes to about $100. It's not a typo, it's $100. And that's because we just leverage spot instances for all of this, and we spin them up only when we need it, right? So these 400 analyses come in, we spin up servers for a brief period, shut them down, and they're gone. So that gives you a sense of what the ROI looks like of this. And this is one example of many where we use this dynamic nature of the cloud to automate decisions that previously humans had to do. So with that, I will stop and I'll happily take any questions you might have.